Okay, so the topic has been the Cartesian plane. The Cartesian plane that is produced from two copies of the real line, x and y. Okay, so the main idea is your ability to plot points based on two numbers that's applied to you, as well as vice versa. Vice versa meaning that you have a point, you find two numbers, as we did over there. So I circled the number over there in orange at the top, and then I was able to find its coordinates. Its Cartesian representation. How I went vertically towards the x-axis. That's how I found 1, 3, and I went horizontally, and I found the other one where the other 3. So well, let's pick a different pair of numbers. So I could pick, say, if I pick this number, this location over here. How do I find its coordinates? I'll go vertically to get this 4. So that's the first number. Okay. And then I go horizontally until I hit the y-axis, and that gives me the second number, 1. Okay, so that's the plan from a location, literally location that you put a finger on the plane, and to find those two numbers. Okay, and then conversely, we're gonna work both ways. Conversely, you are given two numbers, so once again, so this was, if I may put it this way, so I started with a point and then worked my way like this towards these numbers, okay? The order matters. 4 first, 1 second. Okay, and then vice versa, I might start with, say, two numbers are given to me. Numbers. Here, say, -2 and 3. These two numbers are given, and then I'm supposed to, as you can see, I put them away from the xy plane, so there would be no confusion. So these are just two numbers and nothing else. So these two numbers are given to me. I'm supposed to find the location of this point. Okay, it is literally works like a map. So you say this longitude, this latitude on the face of the Earth, and you find the actual location. You can actually travel to that spot, and let's say that this is where it is. So it works out the same way with the Cartesian plane, except, well, the difficulty with the Earth is it's round. This one, fortunately, it is flat. So everything, just like the rest of the Earth. Okay, so -2 and 3, I identify them based on that notation on the right. I identify the first number as the x-coordinate, the second one as the y-coordinate. Do it one by one. So once again, I take this -2 and I find it on the x-axis. It is x-coordinate, so x-coordinate is right here. Okay, and I draw a vertical line through it like this. Okay. Now I look at 3, I find it on the y-axis, as we already have, like this. So that's my 3, and I draw a horizontal line through it. So what is so special, horizontal and vertical? It is in fact the line that is parallel to the other axis. So on the y-axis I go parallel to the x-axis. On the x-axis, from the x-axis I go parallel to the y-axis, which means that it really doesn't matter how my axes are located with respect to the piece of paper. I could draw that coordinate system diagonal, and it works out exactly the same way. Okay, so like I said, it is, you take a piece of paper and what ultimately happens is you supply it. You start with a piece of paper and then you supply that piece of paper with that coordinate system. Okay, which looks like a bunch of you can think of it as a lined paper. Okay, so then as you can see, I have two lines I found in that manner, and then their intersection is that point. Okay, so that is a point P that I have found for my coordinates. The two coordinates produced this point. Okay, so back and forth from two coordinates to the point and back, and certainly I will recover the same two numbers if I try to carry out the process in the opposite direction or opposite order. Okay, so that's the Cartesian system. So I used intentionally. I used the integers only, even though the dimensions x and y they don't have to coincide. But the simplest case is you take integer numbers, and then what you're looking at is a line paper. Okay, line paper. So that all you have to do is just travel along those lines. So you already see a line paper, which is actually underneath the what I'm writing on. I wonder if they have ruled paper. I can actually choose if I want to. You see it? It is a kind of thin, but it's there. So can I light blue? How about red? Now you still can barely see it, but it's there. So line paper, except with numbers attached to every the x is identified, and numbers are assigned to each of those markings on these two x's. So that's the key, like this. Okay, so you may see line paper elsewhere so it's on maps, right? So you see line paper with numbers. What else? Can you think of anything else?
Blueprints.
What?
Blueprints.
Blueprints. Okay, so anything you're making, you might need you do it relative to a certain coordinate system. In fact, if you try to do 3D printing or any kind of printing, in a way, there are coordinates there hidden. Otherwise, it's not going to. How do you explain to the printer what to do? You gotta tell me the coordinate of that point where you put some piece of whatever plastic. The only difference is that you're going to need the third coordinate. So this is we're talking about two dimensions for the time being. Maybe I don't know. I think I've seen maybe like a transparent piece of plastic with the grid, and you superimpose it on things. Well, it's old-fashioned, obviously. And for example, measuring things, not length. So you only need a ruler to measure length. So what do you measure with a grid?
Two variables related to each other.
Yeah, that's not exactly what I'm talking about. What?
Location.
No, locations. Yes, you could. Yes, but what's something practical? There, you see, there is no. This is it does give you a location and relative to the grid. But suppose you have something on a piece of paper and you want to measure it, and you measure it with a grid. What would that be? How about areas? You have some complicated figure on a piece of paper or maybe an object. You put the grid on it and you just start. You count the number of squares, and roughly that will give you the area of that complex object. So that's used to be done a long time ago. So in this manner, like this. 1, 2, 3, 4, 5. So, well, let me. So maybe you have an object that looks like this. Complex object. So how do you count it? You put a grid on top of it and then count how many full or partial squares that you can see. Well, best I can do like this. Okay. So with some degree of accuracy, you can tell what the area is. Okay. Okay. So, but that is we will review that. We'll come back to the Cartesian system for studying geometry of things or whatever you draw on a piece of paper. You can study it with the Cartesian system. But our interest right now is functions. So that's where we are heading next. And so as I mentioned before, so the Cartesian plane also known as the XY plane. Well, there might be other names. Notation is frequently used R squared. So remember that R by itself, R is a line. R stands for real numbers, R, and that is like our grid, like this. Here we have two of these, and that is why we call it R2. Two copies of the real line, put together in this fashion is called R2. Okay, the Cartesian plane, the XY plane, also sometimes it's called the Euclidean plane too. Okay, so now this is where graphs live. Okay, graphs of functions, as we just discussed last time, but also relations. Okay, so just to refresh your memory, functions. And these are relations. So relations contain functions. Every function is a relation, but not every relation is a function. Okay, so we'll be specifically looking at relations that are not necessarily a function. One of them we already saw, and that was the problem about the, I keep coming back to that, of the farmer. And so he was building our enclosure, and let's change notation for our convenience here. X and Y are the dimensions of his enclosure, and then there was a relation between them, literally a relation between them, because the length of the perimeter or the amount of fencing material that he had was fixed at 100. So we concluded, remember what it was, 2x plus 2y is equal to 100, or x plus y is equal to 50 was our relation. We then proceeded on to turn it into a function, but for the time being, we'll suppose that we do not do that. Okay. Okay. So there's no s here, just a single relation. So we actually we plotted it. Let me point it out. This is how we plotted it. Remember this? So width and depth, horizontal and vertical, and we have all possible combinations of width and length between 0 and 100, but the only one that marked are the available. These are the only one that satisfy the relation. We use it as a restrict. We said restriction condition, but the technical term would be a relation. Oops, a relation. Okay, so and then in a way, this is the XY plane. Once again, it turned out a little bit wrong, but it is still the XY plane. So as you can see, the only trouble is that the vertical axis is upside down, but it's still the same thing. It's just the nature of spreadsheet. It spreads down, not up. Okay, so but it's the same thing. Okay. Cell phones, please. Excuse me. But now we have plotted it. Let me plot it the way we just done it a minute ago, based on our Cartesian plane. So let's plot it the way we have. Okay. So plot its graph on the XY plane. So what does it mean to plot the graph? Is plot. So what does it mean? Means this. Plot all points XY that satisfy the relation. That's exactly the way we did it over here, except now we'll just turn it upside down so it fits more into our way to present the XY plane. Okay, so I will plot it in that manner, like this. So x here, y there. The relation is x plus y is equal to 50. So how to plot it? So this is not how. This is what. What is the graph of a relation? And that's what it means. It's all points that satisfy the relation. It's not how. How, these would be the second question. But let me try to Let me try to do it carefully. Okay, so this is, it should be here somewhere. In fact, I can point out that initially in the way we have described the situation is both of them run between 100 and 100. Okay, so it means that where my graph will be located on the xy plane, it means that the x will be between 0 and 100. Okay, it will not go to the left or to the right, and neither and y-axis will not also go beyond 100. Okay, what does it mean? I can roughly now point out where my graph lies. It will lie. Where does it lie? We are plotting all x's and y's that satisfy the relation, but the relation has a restriction on the domain and codomain. Okay, so x and y run between 0 and 100. So what does it tell you about the pairs of points? If both x and y lie between 0 and 100, what does it tell you about the location of the graph?
It's going to be restricted in that area.
The area, it is in fact a square, right? So it will be here somewhere entirely. So if we, that's what happens if when we restrict the two sets that are in relation with each other, we make them smaller or larger than, assuming that it is some kind of both of them are integrals. If both of them are integrals, then the location, the possible location of the graph is a square or a rectangle or something like that. Okay, so it will be here somewhere. We already know how to plot it, but we know the answer. But let's pretend that we don't know. So how do we plot it? And the answer is kind of awkward. Well, I have points here, so let's see. It's a little bit off. 1, 2, 3, 4, 5. Okay, let me change this slightly. So say 100 here, 100. Okay, so I can utilize these markings. Okay, so my square then is this. Oops, that's not working right. 100, and this is the other one. Okay, so my square is this. And as you can see, I have 5 markings horizontally and 5 vertically. Okay, so I have my grid already. Which means that the most natural way to try to plot it is check out, verify every point on the grid just the way we did it over here. Okay. So well, I'm trying to reproduce this picture pretty much. Okay. So I have, as you can see, these values. How many I have? I'll have a lot of possible values of x. So like these. So these are at 20, and then these are at 10 at a time. Similarly here, I cut them in 5, and then I cut them in tenths, like this. So it means that there is 11 here, 11 there, and it gives me 121 possibilities, which is quite a lot actually. So, but that's what we did exactly last time, and the how it was entirely trial and error. Okay, so there are these points, in fact more than that, and we just go one at a time and ask ourselves, is the condition satisfied? So trial and error. So take a point, x, y, so that's the plan, and ask, do these two satisfy the relation? Satisfy the condition. So in other words, are they related to each other? Okay, and then there are two possibilities, yes or no. Okay, if it is yes, plot it. No, don't plot it. Okay, so that's pretty much how it works out. So every single intersection of those two lines, 121 points, have to be looked at, plugged into the equation, and then you tell whether or not it works or not. So fortunately, the relation is very simple. X plus y is equal to 50. So so if I start plotting them, I'm going to have 0 and 50. Remember, we already did it. So 0 and 50, 0 and 50 here, 50 and 0 over there, right? So 0 plus 50 gives me 50, 50 plus 0, so 50. Then you have 30 and 20, 30 and 20 here, 20 and 30 here, right? So so this one is, let me mark them. So 50 and 0, 0 and 50. Okay, so 30 and 20, 20 and 30. Okay, so one by one, and then there are these. You will discover more, but let me actually if we are to be honest, you actually do it like this. Say 40, 40, 40, 40, and the answer is no. So don't plot it. Okay, this one is also no. And then I check all of these points elsewhere, and they all give me no, and so they're not part of the graph. No, so no means not part of the graph. Okay, while this one is. So is part of the graph. It is very inefficient, but that's the matter of principle is that's how it works out. And then if you have enough points, you might be able to guess what the graph looks like. 30. Oh, okay, I didn't put this circle in the right spots. These are not right. Okay, so 30 and 20 is here. Okay, and over here 20 and 30 is over there. Okay, so these are the points. So I have to fix it. So not this. Okay, so then they do appear to be located on a straight line, which we noticed before, like this, right? So this is just a more appropriate standard way to represent the Cartesian plane. Okay, so but otherwise it's trial and error, and then followed by some kind of a educated guess. So trial and error, points here. The guess is this is a straight line. We didn't have to worry about this when we did was solving this problem, but if we're now talking about relations, these are one of the simplest relations. These are the function involved is very simple, x plus y is 50, and so these are the ones we want to understand first. Okay, so it is indeed a straight line. Why is it? How do we know it's a straight line? Now this was a guess. Now can we explain it? Or rather, can we provide evidence, or we can simply prove that it is indeed the case? How do we prove it? X plus y is equal to 50. How do we know it is a straight line? Its graph is a straight line. So take x plus y is equal to 50, and what do we do with it? What? Well, that's what we have been doing, and we got like 10 points or so. They appear to be located on a straight line, so that is certainly that's what data tells us. It tells us that the points seem to be located on a straight line. Then, if we want to be precise, and there are infinitely many points there, so we all know only some of them. The part of the data it's only limited. So can we make it precise so that we know for sure that it is a straight line? So what do we do with the formula? The formula x plus y is equal to 50 is our relation. So what do we do with it? Yeah.
We'd have to give a reason like from 0 to 50 on the y-axis or 0 to 50.
Well, yeah. Well, I guess it's not going to be a full straight line, right? Because it's infinite, so it's not going. If this one's supposed to be limited to the square, so and the actual straight line is an infinite, so that's the language is slightly off. So it's a line segment. What I'm saying. Was a suggestion there? Yes.
I was going to say turn it into a linear equation.
Right. So in other words, solve for y. Solve for y. So that way we can refer to something familiar from the past. So solve for y, which produces y is equal to 50 minus x, or negative x plus 50. And this is what we know from the past, and we will. So this is known as a straight line. Okay. I mean, if you're not sure, you can certainly remember what these two numbers, -1 in the beginning and 50 at the end. You might remember what they actually stand for. What do they stand for? What's 50?
The y-intercept.
It is the y-intercept, and the other one?
The slope.
It is the slope, right. So we will review these concepts, but at this time, that's to be remembered. So the coefficient of x is called the slope, and the y-intercept is the last that term that has no x in it. And you can see it on the graph that the last one, if you just circle it somewhere. This is the y-intercept, right? It is where how high it crosses the y-axis. That's hence the name. So okay, so let's look at it in more general. So now we turn to algebra and just look at all possible linear relations. Okay, so linear relations. So once again x plus y is equal to 50. Okay, and then certainly x plus y is equal to 1. 2x minus y is equal to 3. All of these are linear relations, but there are simpler ones, and so I think we will start with those. And that is, how about this y is equal to 3? So as you can see, there's no x. No x present. Okay, so which might be confusing unless the language already, the description that precedes this formula tells you how you should look at this, how should you should interpret this formula, and you should interpret it as a linear relation between x and y. So the relation between x and y, and there is no x, but in the formula there is no x, but that's okay, because we know that's a relation between x and y, so we still speak of graphs. So this relation will be on the xy plane. So let's just follow the same idea as before and plot it point by point. So once again, we look at all the possible values like this, and then going on and checking out the values that do or do not satisfy the restriction. So this is the restriction is to be verified. So every pair x, y that we pick here somewhere has to be tested. Yes, no, yes, no. So and once again, if it satisfies the restriction, it is plotted. When it does not, it's not plotted. Okay, so starting, let me start on the x-axis. Start with the x-axis. So 0, 0, does it satisfy the restriction? 0, 0 means y is equal to 0. So no. Y is equal to 0, not equal to 3, no. Okay, I move on to the next one. Okay, here the point is 1, 0. Still y is equal to 0, still not equal to 3, still no. So once again, red dot, it's not part of the graph. I keep going, and then I have 2, 0, and every point on the y-axis will have y equal to what? 0, so not equal to 3, so no points here. Okay, and then well, how would you? So every point on the x-axis is not on the graph. Then you take one step up. You look at these points. Okay, so once again here, y is equal to 1. Once again, not equal to 3. No points. Once again. And then you keep going until, well, that's once again the same problem here, until you reach actually this location, you will not get any points. So y has to be equal to 3. What does it mean? It means that it doesn't matter what x is, but y has got to be equal to 3. If it is, then we plot it, otherwise we do not. So here, y is equal to 3. So all points here belong to the graph of our relation. Okay? None of them will. None of the rest of them will satisfy that relation. So it's a very simple relation. As you can see, x is not, the relation is between x and y, seemingly, but in reality, we're just talking about restricting one or the other or together. In this particular case, there is no restriction on x. That's all, and that's why we are moving horizontally freely, because that's the direction of x. So from the point over here, which is 3, we can move freely left or right because it does not change the value of y. Okay, so we are getting everything, and the rest of the points are not on the graph because y is not equal to 3. So all of these points are gone. They are not part of the graph. Okay? Okay, so that's a very simple example, and you can see that we then have a bunch of linear relations. Every horizontal straight line is in fact the graph of a linear relation. So that's one, and then you have another one, and you have more and more. All of these are graphs of different equivalence relations, linear relations. So these are graphs of linear relations of a special kind, and that kind is y equals something. No x. Okay. No. Okay. Okay. So at the other extreme, we only pose a restriction on x. X is equal to 2. No y present. Can you guess what the graph looks like? A vertical line, right? So once again, the x is fixed, y is arbitrary, so you can go vertically with no limit. So all of these will be relations of this linear relations of this special kind. So it's like you can think of it as a fence, which is what I'm plotting here. It's like a fence made of these vertical lines, but there aren't many of them. So let me first write this. So graphs of linear relations of the kind x is equal to k, no y. Okay, so x equal 2 is one special here, say this one. So as you can see, these are lines are parallel, which means that they never intersect. Okay, just like those horizontal ones. But also you can draw through every point on the x-axis. So 0, you can pick 0, 1, 2, 3, but also every value in between, you can pick that point and draw a vertical line through that point. And so there aren't many of them. They are kind of a dense, so in the literal sense. So if you have two lines, you zoom in and you can still squeeze one more line between them. And then you zoom in more, there is gap between them, you squeeze another line between them. And so there is that process. Process is infinite, just like that. On a ruler that has you start with an inch, and you have lines. Okay, then you have a half inch, another line, so eighth, fourth, eighth, 16th of an inch, and then every one has a line in it. Okay, so we already have a bunch of typical, if I may put it this way, linear relations when both x and y are present, and these are sort of extreme relations that y is not present. So we want to embrace them all. We want to embrace them as relations rather than functions, even though, as you remember, in this last example, we went in the direction of functions because they are easy to handle. But look at the very last relation that we're looking at. What is so special about this relation x equal 2? In comparison to y equals 3, x equals 2. So compare. One is very different from the other. From the point of view of functions. That's the hint. Well, suppose x is the input and y is the output. These are two different ones. What I'm saying is, can we build a function from one or the other or both? Yes? Which one? Or both? Both? No. No. Y is equal to 3 we could build, as long as we identify x is the input, y is the output, then they become unequal. And then these two are they are distinguishable in the sense that the one is a function, the other is not. Y equals 3 is a function because it is simply, we just say whatever x is, the output is 3. There is nothing wrong with that. So you can have a diagram like this. Something is happening here. X comes in. No matter what comes out, no matter what comes in, 3 comes out. It's called a constant function. However, x equal 2, think about what x equal 2 means. It means that that so-called independent variable is actually fixed. So and then there is no word spoken about what y is. So it is not a function. And because if you look at the graph, it appears that there are many. So suppose I'm looking at 2. This is my input. How many outputs do I have? All of them, all right? Right. All of these are outputs, and that's not allowed for a function. Function can only have one output, right? So if we decide that there's only one input 2, then there should be only one output. It is a very uninteresting function, and even then it's not working out. As you can see, we have infinitely many outputs. So this one is yes, a function. So in other words, can we solve for y? Of course we can. It's already solved for y. This is not a function. Can we solve for y? No, because there is no y. Okay. So that's the main difference. And then the rest, the question becomes, what about the rest? As you can see, we have a bunch of them. So we'll take a general look at these and decide what's happening here. So this is the general formula, the general linear relation. Well, linear relation, you certainly can guess why it's called linear, because the graph is a line. Okay, so ax plus by is equal to c. That's the relation. So x and y are those two variables. and ABC are fixed parameters. Okay, so in that particular case, x equals 3, x equals 2. What does it mean? It means that A is equal to 1, B is equal to 0, and C is equal to 0. Y equals 3, the other example we had, A is equal to 0, B is equal to 1, and C is equal to 3. I'm sorry, this one is 2. Okay, so as you can see from this general equation, we can get the two extreme cases, extreme degenerate cases, if you like, of linear relations, as well as the one that we had, what was it, x plus y is equal to 50, remember this one? So here A is equal to 1, B is equal to 1, and C is equal to 50. So all three examples that we have seen so far, linear relations fall into this category. You just have to choose the A and B correctly. One thing we have to be very careful about, and that is, there is one extra restriction that on ABC, not every combination of A, B, and C is possible. So give me an example. What if A is equal to 0, B is equal to 0, and C is equal to 1? What do I get? Substitute, what do I get? I'll just replace A. If I replace A with 0, well, let me just carry it out. 0 times x plus what? 0 times y is equal to 1. Okay, so simplifying, what do I get? 0 equal 1. Okay, what's its graph? What? Oh, you don't ask, tell. No solution. Okay, no solution. Right. So what is it? What's the graph then? What? What? Yes. That's right. So there is a word for it. I mean, if there is nothing on it, it doesn't mean that it's not. It does make sense. It makes sense. So we should be able to tell what it is. So what is it? The empty set. Yes. The empty set. Just like 0, it is a meaningful. You don't say nothing. You say it's 0 because it is actual number. It is informative. When you say nothing, it is like you give up and you don't have nothing to say. But you say 0. You say the empty set. It is specific. You say that well, it is something, and you know what it is. So the point of this this example was to point out that the graph of this particular linear relation is in fact the empty set, which is not a line, which means that it's not a linear relation. That's why a linear relation has an extra restriction that either A is not equal to 0 or B is not equal to 0. So you cannot have both A and B be zeros in order to have a linear relation. So the formula is the same, but the restriction is on the coefficients A, B, and C is that not both of them are equal to 0. So what remains is examples that are more reasonable. So AX plus BY is equal to C. What we can do with it, we can produce functions. So functions can be produced from this. Okay, we have a couple of minutes left. So we can produce functions. So if, how about B, case 1? B is not equal to 0. What does it mean? It means I can divide by B and simplify everything, right? So I divide by B, And what do I have? I have a over b x plus y is equal to c over b. And so I can actually solve for y. So y is equal to a over b x minus plus c over b. Okay, so that's once again the standard form of the standard form, also known as the slope-intercept form, right? Slope, the first number, x-intercept, the other one, y-intercept. So the standard form or slope-intercept form. Okay, so that as long as b is not equal to 0, we can represent the function in that manner. On the other hand, what if a is not equal to 0? Then we divide in a similar fashion. We divide by a, and then what we have here is x plus b over a, y plus c over a equal to c over a. Okay, and once again, what do I do with this one? What do I do with this one? I don't solve for y, but what else can I do? I can solve for x. So from every relation, if you can find a function there, it might be one or the other. You can have y depend on x as case 1, or you can have x depends on y. So x is equal to negative b over a, y plus c over a. The same form, except once again, x is the instead of y is the dependent variable. Okay, so the function is, well, what is input, what output? So this is the input, and this is the output. Okay, and now, well, it's everything is flipped. But the rules are still apply. How we plot the graph of this relation, same point by point, and we do know that in either case we know that the end result is a straight line. Okay, so I'll stop here. Homework due tonight.